Hello and welcome to a brief demonstration on graphing rational functions from their algebraic formulas. The objective of this slideshow is to demonstrate how to obtain the graph of a rational function from an algebraic description. Some materials for review include finding domains of rational functions. This is done by setting the denominator equal to 0 and solving. We shall also want to determine the intercepts of rational functions. X-intercepts are found by setting the numerator polynomial equal to 0 and solving. We're going to double check to make sure the value is in the domain. And we're also going to find the y-intercept, which is found by substituting x equals 0 into the rational function and simplifying. Again, double check to make sure that 0 is in the domain. We're going to want to find asymptotes of rational functions, and this refers to all types of asymptotes, the vertical asymptotes, the horizontal, and the oblique asymptotes. Now, vertical asymptotes are values that make the denominator 0, but not the numerator. Horizontal asymptotes occur when the degree of the denominator is greater than or equal to the degree of the numerator. If the degree of the denominator is greater, then y equals 0 is the horizontal asymptote. If the degrees are equal, then the ratio of leading coefficients is the horizontal asymptote. Oblique asymptotes occur when the degree of the numerator is greater than the degree of the denominator, and these are found by performing division and consider the quotient. The remainder will have a degree strictly less than the denominator via the division algorithm. And one other thing that we're going to determine is where the holes are located when they are present. Holes occur when a root of the denominator is also a root of the numerator. This will lead to a 0 divided by 0 form, which is indeterminate, not undefined. So indeterminate means we have to investigate further, and the steps to do that are listed here. We're going to reduce the rational function by canceling the duplicated factor. We're going to substitute x into the reduced form. This x value is the x value that gave the 0 over 0 form for the original rational function. If a numerical value occurs after I do this substitution, then we have a hole in the graph. The x-coordinate is this value that makes both the numerator and denominator polynomials equal to 0 in the original rational function. The y-coordinate is the value that results when using this x value in the reduced form of the rational function. Some notes on the following examples. The generic symbols used in this presentation when needed are r of x for the rational function, n of x for the numerator polynomial, d of x for the denominator polynomial, and r bar of x for the reduced form of the rational function. And these are all capital letters. Now, if you have trouble remembering the conditions for horizontal asymptotes or oblique asymptotes, you may go ahead and perform division of the rational function. The quotient is the horizontal or oblique asymptote. The guidelines for the horizontal asymptote and the oblique asymptotes are merely shortcuts to circumvent this arithmetic. So you may think of horizontal asymptotes as a very, very special case of the oblique asymptote. And finally, complex solutions of any kind are not considered here as part of the graph because we are graphing in the real plane. If a complex number is required to make either the numerator or denominator equal to 0, we discard it here. So let's take a look at this example. R of x is equal to x minus 1 divided by x squared plus 1. And we're going to find the graph of this rational function. So we're going to proceed as follows. We're going to find the domain. So we're going to set x squared equal to 1 equals 0 and solve. And when we do this, we find that either x equals I or x equals negative I. And these are complex roots. And these are the only numbers that make the denominator equal to 0. Therefore, the domain is all real numbers. The vertical asymptotes are the real numbers where the denominator is 0. but there are none here since the roots are not real but complex. Therefore, there are no vertical asymptotes. And because of the same reasoning, there are no holes in this graph either. So this means we have no vertical asymptotes and we have no holes. Every real number will be satisfactory in substituting this in. Now, to find the horizontal or oblique asymptotes, we're going to compare the degrees. So the degree of the numerator is 1. The degree of the denominator is 2. And so the degree of the numerator is less than the degree of the denominator. Therefore, y equals 0 is the horizontal asymptote. And because I have a horizontal asymptote, I cannot have an oblique asymptote. And this is a result of the division algorithm. Remember, the division algorithm states that when you perform this division, the quotient and remainder polynomials are unique. So because we have a quotient of 0, because the degree of the bottom is bigger than the degree of the top, that means that there cannot be any other quotient. So y equals 0 is the horizontal asymptote, and again, there are no oblique asymptotes. So let's take a look and see what we have of the graph so far. So right now, what we have is this horizontal line that's dashed on the x-axis. Remember, asymptotes are not a part of the graph, so we use dashed lines to represent them as guidelines for the graph. So right now we don't have a whole lot, but we will in just a moment. Now we're going to find the intercepts of this rational function. The x-intercept is found by solving x minus 1 equals 0. That's the numerator. So we find that x equal 1 is going to be the location of the x-intercept. But we also know that this root has a multiplicity of 1. Therefore, the graph is going to cross the x-axis at this point, 1, 0. The y-intercept is found by evaluating the rational function at 0. So when I plug 0 in, I get negative 1 back. So my x-intercept is 1, 0, and the graph will cross the x-axis at this point. And the y-intercept is 0, negative 1. So let's put in this information and see what I have. So when I plot these 2 points, this is what I end up with. So I have a point at 0, negative 1, and I have a point at 1, 0. And I know the graph is going to cross the x-axis at 1, 0. So at this point, because I know that every real number is allowed into this function, and I know the long-term behavior from the horizontal asymptote, and I know some specific points that the graph has to go through, I'm actually ready to sketch what this graph looks like. So let's go ahead and do that. All right, so at this point, we know that rational functions are continuous over their domains. So we know that there's going to be a connection between the y-intercept and the x-intercept. So let me just go ahead and kind of sketch a graph that connects those 2 points. So I'm going to kind of do it this way here. Now I know that at the point 1, 0, my graph is going to cross the x-axis. So it's going to cross, and we'll just go ahead and show that it crosses here. All right, now that we have it crossing, we're going to use the definition of the horizontal asymptote. We know that as I go further away from the origin, my graph should be getting closer to this horizontal asymptote. We also know that it's not going to hit the horizontal asymptote again because it's already hit it at the location 1, 0. That was the root to the rational function. So I know that somewhere it's going to turn back around and it's going to get closer and closer to that horizontal asymptote, but it's never going to get there. So right now, a rough sketch of this is going to look something like this. So over here now at the y-intercept, I'm going to go ahead and draw the second half of this graph. Now, what I do know is that it's going to go through this y-intercept, okay? And then I know that as I get further away from the origin, it has to get closer to the horizontal asymptote, this dashed line here on the x-axis. So I know that I'm going to kind of turn around and I'm going to get closer to that graph, y equals 0, as I go further away from the origin, but I'm never going to hit it. So this is just a rough sketch of what the graph looks like. Now, more precise graphs would require either technology or additional points being plotted. But right now, we're just sketching the graph. So we're going to see what the graph looks like according to technology. So here is what the graph looks like using technology. So here we can see that we have a pretty accurate depiction of what's going on from our sketch. So let's take a look at our sketch again. So from our sketch here, we do actually see that the behavior is being mimicked. Now, as I mentioned before, more precise behaviors, specifically around the minimum value here and the maximum value here, this can be determined either by using calculus tools or it can be determined by plotting more points. But as far as the overall behavior of my sketch goes, it is actually pretty consistent with what technology is showing us. So in this example here, we were able to kind of deduce the overall behavior of this rational function. So rational functions do not have to have holes or vertical asymptotes in order to be graphed. And this is an example of one that doesn't have either of those characteristics. Thank you for your time and attention.